Alright, time for another draftphysics.com video presentation. So, part 2 of the photon. And so, I guess we'll go over some description of what a photon might actually look like, sort of based on Einstein's description as some sort of starting point. But he doesn't really draw things, so it's not as useful, I don't think. And it's just making the photon very physical and mechanical. So there's not going to be any part of it that's not discrete and has a real component. And the real component being the important part of that is momentum. And that became more important to Einstein a few years later, after he first wrote about photons, maybe 7 or 8 years later. He added the idea that they had a certain and specific momentum, and that this causes recoil in atoms and all kinds of things like that. So it made it even more of a physical description. So I will attempt to take that further. Not that any of this is based on Einstein, because it's not. It's just based on my perception that photons were always in the form of a ray, and that the ray had components. Now, originally I might have thought the ray contained the idea of a photon, but then when you think about radio waves and you think of this being a photon, 10 miles long, you say, no, there's not some piece of glue or something that's 10 miles long. And so that vision of what a frequency would be didn't really work. And it would works so much better, is the exact opposite, or inverse, where the component is at the frequency and the frequency is the empty space between it. So the 10 miles is this distance here between the event of the energy quanta, or like quanta as Einstein described it. So the photon isn't this. The photon is what these quanta add up to. So the idea would be is that you'd have some number of them, and I've been using 3, some minimum. It's got to be more than 2, right? Well, it has to be at least 2, or you couldn't have a frequency. So whether it's 3 or 4 that make a photon, who knows, could be 10. But regardless, the idea that the photon is this composite object that in a specific amount of energy equal to this much has to hit something. And the simple idea is that connects this to the math, the idea of H bars and all of that kind of crap, making it a Planck quantum of energy. It's just the simple idea that in the time component is where you increase the energy component. So the more I can collapse this into a smaller amount of time, the more I increase how much energy it has, in the sense that the volume is in this smaller amount of time, which means the volume has essentially got a higher velocity. You could think of it in those terms, or you could just think of it in the terms of, if this was energy you were hitting a system with that was very rebounding, that was very reflexive, that the less time you give it to reflect, the less time you give it to, like a piece of it hits, a ball hits, the object swings into with the energy, but then swings back. And so if you know that you're hitting before you could ever recoil, then the energy has to keep going into the object. So this gets to the photoelectric effect, and the fact that the low frequency doesn't do anything. It's not till you get to a certain frequency that you have the linear line, where you have a proportional increase in how much energy based on how much closer the little bits are to each other. So there's a certain point that you're tipping, the thing's wobbling, and there's a point where if you're too slow, you're always going to add energy when it's tipping in the wrong direction. And there's a certain point you reach where you're always in the positive direction, because it never tips back. And that would be ultraviolet light, is where that tipping point is, where now you're hitting it so fast that the energy has to go in is it can't reflect back. And so it's just that tipping point argument. And the faster you put it in, the less it slows down before you put more energy in. So you're putting more energy in before it can possibly reduce its velocity, and then you have to add velocity, and it reduces velocity, and you have to add velocity. So the more compact the quanta, the more energy gets delivered, because the system doesn't slow down. It doesn't drag. It defeats the drag by doing it quicker. And obviously, these are much rarer photons, the ones that have the very high frequency. And so that also makes sense in the sense that they're not the easy ones to make. So the higher energy comes with the rareness. Okay. That you have to make these by having high pressures, a high amount of force to be able to get the energy to be in so close a proximity requires you to push a lot against it. So if the idea is that every time this happened, an electron moves forward, the idea would be is that on one side of the universe it's going to reflect energy. That means it's going to make one of these higher frequency events. So if I pushed into, say, red light, and I push an object into it, the light's going to reflect as bluer light. Now on the opposite side, it's going to see a retracting electron. And so the frequency coming in is going to be expanded. So the distance between the objects that would be hitting the back of my hand, the distance between them will increase. And the distance between them for the forward hand is going to decrease the distance between them. So I'm going to be blue shifting forward and red shifting behind. And it would take a tremendous amount of speed in an electron to create something like a gamma ray. And the more common speeds for the electron would be the more common things like infrared light and microwaves and radio waves, much easier to produce than the more compressed, higher frequency bits of force. So electrons are essentially creating photons out of what already exists in the field. So it would be the same argument I would make for a magnet. A magnet isn't producing a field. A magnet's just reflecting the field that comes in. Different. So what comes in is changed, but it's not more, it's just different than what went in. One color goes in, another color comes out, kind of idea. And the electron's doing the same thing every time it moves. It's adding energy to one side of the universe, and it's subtracting energy from the other side. It's relaxing one side of the universe, sending the slower wavelength, and the other side is sending the higher wavelength, the higher frequency. Better way to state that. So this would explain a photon. It would explain the photoelectric effect. It would explain that, yes, so this is a photon. Now, the other part of what photons do is polarization. So you need an added feature to say, okay, well, polarization is basically this, dot, 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 except the dots are on different levels. So the photon is really little pieces moving, but they're in different vectors of space. So the frequency, okay, you almost see that. The frequency is this distance, and the polarization is this distance. So you can sort of see the polarization be going this way, and the frequency is going in the other dimension. So this is your frequency, this will be your polarization. And so photons can have any of a number of different polarizations. And so you can make a model that works, that satisfies the conditions, and then it's just a matter of explaining how it's affected by different filters or different obstacles you put in the way of the photon. So the simple explanation for what's happening in the double slit is that this, idea of a distance between these little pieces, and what you're basically saying is that you're running this photon through the obstacle course of a bunch of electrons on the surface. And the electrons on the surface are either going away from the surface or into the surface. That's what the pressure is doing. So they're either going in and out of a surface. And so that it perfectly explains that you're sending the photon in this way. It can hit an electron that's going that way, or it can hit an electron going back in. And depending on which electron it hits, will change the direction of the electron. And now it will shoot the photon that way or that way, in the sense the electron will move in that direction, compress energy in that direction, and send a bit of force, a reflection off the electron that will duplicate the bit of force that hit the electron. It'll just change the direction. So on the surface, you're basically saying you have this in and out action, which is going to cause scatter in those specific directions. Okay, so it's going to go, the scatter is going to be perpendicular to the surface. Well, yeah, perpendicular to the surface. And that's why it doesn't go in any direction. That's why it doesn't, the pattern doesn't go up and sideways in a bunch of directions. It goes pretty much in one direction, perpendicular to the surface. So if you make a round opening, it goes in all directions. You make rings because it's perpendicular to all those round surfaces. All right, so that might be enough to start with. And then when he gets into talking about the quantizable mathematical component, you'll sort of get what the point is that what Einstein basically said is that these light quanta make a photon. The elements create the photon. The photon isn't one of these light quanta. The photon is made of what would be called light quanta or energy quanta. I think that'll work. Alright, so we'll see where we are.
Because if light is a wave, no matter how weak it is, it should hit the entire screen. It cannot hit certain parts of it. Waves don't hit certain parts of it. In fact, how can it hit just...
So again, that's just as simple as any time you have a beam of light or something that's confined, wave theory doesn't really work because waves intrinsically have to spread, and laser beams don't spread dramatically, and rays of light don't dramatically spread, and clearly you can transmit photons in very straight lines over very long distances.
Just one. For example, if you make it weak enough, you can have a situation where in the whole day you just get one hit. So something is hitting the screen and it's not a wave. The wave is spread out over its full transverse dimension, but this is hitting one point on the screen.
Strong indicator that it is a particle. Now again, it's simple to argue that particles can look like waves, but waves can't look like a particle. So that the underlying feature is that it's in this corpuscular particulate form, and that you're just the illusion of waves is just an emergent property where you're making the particles, giving them an arrangement that makes them appear like they're waving.
So you make further observations and you find out that what happens here is that a certain amount of momentum and energy are delivered during that hit. If you could measure the recoil of that film, you'll find...
So it's all going the same speed, and what it's basically saying here is that momentum indicates that it has to have velocity and mass, so that the quanta, the bit of energy that hits the surface, is a certain amount of momentum, or mass and velocity. So velocity becomes moot because we know it moves the speed of light, and so all you can have is the mass, and what changes is how much mass, how much momentum you're delivering in a unit of time. So the higher frequency delivers the energy in less time, which doesn't mean it went faster, but it does mean there was more of it in a unit of time. So there's more mass per unit of time. And that density is what makes ultraviolet light more powerful or energetic. the particles themselves don't have more energy, but because you're delivering it over a smaller unit of time, it in effect has more energy, because it's, in a sense, even though it's all, the red light's moving the same speed as the blue light, because the frequency is all compacted, the mass is all compacted, it's as if you've increased the velocity, because you're delivering all the mass over a shorter period of time.
And it gets hit, and the momentum you get per hit looks like h bar times k. I'll tell you what it means. This is 2 pi h over lambda. The lambda is your weight.
So it doesn't really make, it doesn't tell you what it means. But anyway, Planck is constant, just this tiny number, and so you're multiplying it by 2 pi for whatever reason. So all of this is sort of abstract. It's really just telling you that there's an elemental amount of energy. It doesn't really matter whether we say the elemental amount is 10 or 15 or 20. It's just that it's always the same amount of elemental energy, and the only thing you can change about it is how much time it happens in. And if you change the time, that's essentially the same as increasing the velocity.
Wavelength, h is a new constant called the Planck's constant. And its value is 6.6 times 10 to the minus 34 joule seconds.
So this doesn't mean anything, just like all the other joule numbers they talk about. So they say the speeding bullet has 2,000 joules, 2,000 watts, but they've never collected those watts. They've never done work with those watts. So those numbers are always just mush. They say the recoiling gun only has 2. Clearly a huge disproportion that you can't make any sense out of it. They say that 1,000 atoms going 1 mile an hour is 1,000 times less energy than one atom going 1,000 miles an hour. Clearly not true.
You also find every time you get hit here, there's a certain energy deposited here. And the energy deposited here happens to be h bar omega, where omega, as you know, is 2 pi f. So here's what I'm telling you.
Which doesn't mean much. I mean, times that. So the f is the frequency in this case. So again, all you're saying is there's a relationship between the frequency and the energy. And so when you deliver the entire packet, that is the photon, the 4 units of quanta, in a shorter period of time, it means it can do more work.
If you send light of a known frequency, a known wavelength, and you make it extremely dim, and you put a photographic plate, and you wait till something happens, what happens is not a thin blur over the whole screen. What happens is a hit at one location. And what comes to that location seems to be a bundle of energy and momentum, i.e. a particle, right?
So it's particles. It's a bundle of particles. And it always is the same number of particles, but they're being delivered in different amounts of time, which means they'll feel like more energy.
When something hits you in the face, it's got energy, it's got momentum. So this film is getting hit at one point by a particle, and what we can say about the particle is the following. It has a momentum. It has the same momentum every time. You get this hit, you get that hit, you get that hit, as long as you don't screw around with the wavelength of incoming light.
So as long as you don't screw around with the wavelength, right. So the momentum changes with frequency. But that's only because of essentially this tipping point argument, where you're really throwing the same rocks. So you can throw rocks at something that's wobbleable. You throw a rock and it wobbles, and then you throw another rock. Well, obviously if you throw the rock while it's coming towards you, you're not going to add energy. But if you always throw the rock when it's moving away, you'll guaranteed to add energy. And the biggest way you can guarantee it is to throw the rock so fast that all the rocks hit before it ever wobbles back. So if you can hit it once and then hit it twice while it's still moving, and then hit it a third time while it's still moving, and hit it a fourth time while it's still moving, and it never slows down, right? It never slows down because you just keep hitting it. Well, then you'll deliver the most energy to the system. And that's really what you're saying, is how much energy to deliver to the system. So the system of the atoms can have the energy delivered. The faster you deliver the energy to the atoms, the more energy the atoms retain.
The momentum and energy of each packet is identical. So it's more than saying light seems to be made of particles. Made of particles, each one of it carries an energy and momentum that's absolutely correlated with the wavelength and frequency.
Right, so it's the energy they carry. The quanta are all the same. You're just saying, again, I'll just emphasize it again, that obviously if I compress the time in which I throw the four rocks are going to have more of an effect. They don't have more energy. Each rock was thrown with 50 miles an hour, but they will be more efficient in transferring their energy if they happen more rapidly. So the more rapid they can hit the object, the atom, the more complete will be the energy transfer.
I remind you that omega equal to kc for light waves. We've done this many, many times. That means the energy.
So again, this is just so arbitrary, kc. So you're just measuring it times, you're multiplying something times a constant times the speed of light. I mean, it doesn't mean anything.
It's h bar omega, and the momentum is h bar k.
So again, the momentum and the energy ends being the momentum times a velocity factor, right? Which just seems kind of redundant. Why would you have the velocity in there twice, right? But it works in the sense that it's really a density argument. So what you're really saying is that you're increasing density, and by increasing density, it's almost as if you've squared the velocity.
Are related by the relation E equal to PC.
So PC would have two components of velocity, right? The speed of light is a velocity. Okay, that's how fast the light's moving. And obviously the momentum has to have the speed of light in it. So you're basically just saying the E equals mc squared. You're basically just saying, that's Einstein's formula. But it really isn't. The velocity and the speed of the event aren't the same thing. So the speed of light really is in there only once. And what you're really just saying is that the faster you can make the event happen is essentially very much like increasing the velocity that's in that momentum number.
So these particles have a momentum which is related to energy by the formula E equal to PC.
And then he'll claim they're particles that don't have any mass, which is just ridiculous. They'll talk about things having momentum when they don't have mass, and then they'll talk about things having momentum when they don't have any velocity. It just makes no sense.
When we go back to your relativity notes from the last semester, you'll find the following relation is true. Any particle, E squared equal to C squared, P squared plus M squared C to the fourth. That's the connection between energy and momentum.
So there's no connection between energy and momentum, and beyond the fact that energy is made out of momentum, and all you're doing again is squaring the velocity. So you could get rid of all these squares and you'll be just as happy.
Therefore, this looks like a particle whose M is 0.
So I don't know why he says, therefore it looks like a particle whose M is 0. Why the M is the only one there? Why he just crosses it out? Why does he say that's what it's okay to do? So it beats the hell out of me. It doesn't look like it has a 0 mass. Nothing looks like it has a 0 mass. There's nothing in the equation that tells me it has a 0 mass. So I don't know why he says it looks like 0 mass.
M is 0, E equal to PC. So these particles are massless, they have no rest mass, and something.
So just nonsense. We'll just ignore that part because there's just no point in talking. There's no PC without a mass. There's no P. There's no momentum without mass.
With no rest mass, if it's to have a momentum, must travel at the speed of light. Because normally, the momentum of anything with mass is mv in the old days divided by this after Einstein.
Right, so we don't need to divide by this after Einstein, okay? The momentum is mv. We don't need to prevent it from going to infinities because it couldn't go to an infinity.
Fine. And if you don't want to have an m, and yet you want to have a p, the only way it can happen is that v is equal to c.
Right. So you're just basically saying velocity squared, and now I don't need a mass. Well, that's just ridiculous. But you can't go c squared anyway. So what's it? Why even talk about it? It's not a possible velocity.
When you have 0 over 0, there is some chance. And nature seems to take advantage of that 0 over 0. These are the massless particles.
Well, whatever. Again, I think in principle, that'll just hurt your brain. It won't make your brain work better.
So these photons are massless particles. So what is the shock? The shock is that light, which you thought was a continuous wave, is actually made up of discrete particles. In order to see them, your light source has to be extremely weak. Because if you turn on a light source like this one, millions of these photons come, and the pattern is formed instantaneously. The minute you turn on the light...
There's no instantaneous. So again, why would he say things like that? There's no instantaneous. So it takes time for the light to get to all the locations and to bounce off and to do all this stuff. But obviously, you're not going to be able to see that each little spot is being hit by particular rays of light, and that's it. Without those particular rays, you wouldn't be seeing the reflection. Every reflection is made out of some ray that came from some direction. And you could see all of that if we could see all of that, but we can't. So it's sort of a moot point. All right, continuing.
The film is exposed, you see these dark and light fringes. You think it's happening due to waves that come instantaneously. But if you look under the hood, every pattern is formed by tiny little dots, which occur so fast that you don't see them. That's why you got to turn down the intensity to actually see that. When you see that, you see the corpuscular nature of light.
Well, I think everybody already knew that, I thought. I just don't know how you could think of light exposing a film in any other way than one little dot at a time. So I'm surprised that people could imagine something else.
But here is the problem. If somebody told you light is made of particles and it's not continuous, it's not so disturbing. Because water, which you think is continuous, is actually made of water molecules.
Yeah, I know, but they're all stuck together, and there's nothing sticking the elemental bits that make up a photon. They're not stuck to each other. They're not attracted to each other, not repelled by each other. They're just forced to be in association with each other by circumstances. But they're not stuck to each other. They don't move collectively. They won't create a wave front. They won't do any of that stuff. They're not gluey. And the reason why water and sound behave the way they do is because atmosphere is forced to be compressed. It means the little atoms are closer to each other than they want to be. And in the case of water, they're glued to each other, physically, actually stuck to each other.
The thing that you think is continuous is made up of little molecules, and in a bigger scale, much bigger than the atomic or molecular size, it looks like it's continuous. That's not the bad news. The bad news really has to do with the fact that if you have these particles called photons...
Right, so the photons aren't a particle. They're a composite object, an object made of elements that are energy quanta.
If it really were a particle, namely a standard garden variety...
you can't have a frequency if it's a particle. The particle would have to be as big as the frequency. It doesn't make any sense. Clearly, the frequency is the distance between the pieces of energy.
Particle, what should you find? If you emit a particle from here, and only one slit is open, it'll take some path going through that slit and it'll come there. So let's say on a given day, 10 photons will come here. Let's say 4 photons will come here, with this one closed. Then let's close this one and open this one. In that case, maybe...
So again, he's sort of playing a game, because this arrangement isn't the way it works. The way it works is this is a tiny experiment, and it doesn't get any bigger 5 miles away. It's still a tiny experiment. The photons that travel a straight line, that aren't interfered with by the slit, travel a dead straight line. They just go straight through, and they don't spread.
3 photons will come here. Let's say again 4. Now I'm claiming that when both are open, I get no photons.
Okay, so he's claiming it, but it really doesn't happen. So again, it's just, that's projection. That's not a fact. That's not a well done scientific experiment proved that they can make photons disappear in the slit experiment. It hasn't really happened.
How can it be that when you open a second hole, you get fewer particles coming?
It can't be, and especially not for photons, because photons really don't interfere with each other. So it can happen with radio reception. You can send two signals, one in phase, one out of phase. One at one phase, the other one at an opposite phase, and those two signals will become undecipherable. So you have two signals hitting the same location, but you can't receive either one because they're out of phase. And if you put them in phase, then you can receive both, but if they're carrying any music, you won't be able to hear the music because the two signals will be canceling each other. Those two signals will interfere with each other. But you can't receive it unless the receiver can tell one from the other, and it can't if they're out of phase.
Particles normally either take path number 1 or path number 2, either through this slit or this slit. So all the guys going this way, they don't care if this slit is open or closed. They don't even know about the other slit. They do their thing. And guys going through this slit should do their thing. Therefore, you should get a number equal to the sum.
Right, and you do. They just don't know that that's what you in fact do. So, because it is a small experiment, they can't really do this closing a slit and opening a slit without creating more surfaces and changing the experiment. But the fact is they can't really cancel the photons that are actually going there. You can just add more, and when you add more photons to your neighbor, then you look darker. So the fact that you can have the optical illusion that something is darker than something else, there's lots of optical illusions that are created where, because of what you surround something with, it looks like it's darker in one context than it is in the other context. And the fact is, it's not any darker. It just looks it.
But you don't. In other words, for particles which have definite trajectories, opening a second slit should not affect the number going through the first slit. You understand that? Particles are local. They're moving along and they feel the local forces acting on them and they bend or twist or turn. They don't really care what's happening far away with the second slit, maybe open or closed. Therefore, logically, the number coming here must be the sum of the number that would come with 1 open and 2 open. How can you cancel a positive number of particles coming somewhere with more positive number of particles coming from somewhere else?
So he's asking a question that's moot because the premise it's based on hasn't been established as an absolute fact. And let's just say, even if it was, you could suggest a phenomenon where if more than one photon hits the same spot, that it interferes with the ability of the surface to reflect the photon because you've hit it with too much energy. So you certainly could make arguments that would explain why 1 + 1 = 0 instead of 2.
How do you get a 0? That is where the wave comes in. The wave has no trouble knowing how many slits are open because wave is not.
All right, so let's understand, but all this is defeated by me just doing the radar experiment. So just take that image that he has and put another slits on the other side, okay, and then have it being a radio antenna. So you have energy coming from this side and you have energy coming from this side. Well, there's no way for those rays or those beams or those waves to now interfere with each other. So they can't interfere in the space. So any kind of wave mechanics is now eliminated as a source of the problem, because obviously the waves will hit the surface both sides. The energy will get to the surface.
Localized. Wave comes like this, it can hit both the slits, and certainly cares about how many slits there are. Because there's only one, that wave will go, it'll have some amplitude here, which is kind of featureless. If that's open, it'll be featureless. If both are open, that'll be interference.
So again, the interference is he's drawing it as if it's in the surface, but clearly it has to interfere in the space. There can't be interference unless this wave interferes with this wave. The two waves have to interfere with each other before they get to the surface. And again, the radio experiment proves that's not correct. That doesn't happen anyway.
So we need that wave to understand what the photon will do. Because when you send millions of photons, and if you get the pattern like this,
So again, I've already established in the part one that what these really are point sources, and the point sources perfectly define why there's what's called an interference pattern, and it's really just a reconstruction pattern. The surfaces break the photons are remade on the surface with components from the different point sources. So the different point sources are all throwing parts, and all you have to do is collect two parts, in phase, out of phase. It's only two parts. So it's either a right wheel and a left wheel. And all you're waiting for is to have a combination of left wheel, right wheel. Left, left won't work, right, right won't work, but left, right will, or right, left will. So 50% of the time you got the right match, you recreate a photon. 50% of the time you have the wrong match, you don't have a photon. But that simple explanation fixes the duality problem of saying which slit did it go through. It has to go by both surfaces. In the case of the double slit, it has to go by all four surfaces.
So you send lots and lots of photons, and you got a pattern like this. Now I'm going to send million plus one photon. Where will it go? We do not know where it will go. We only know that if you repeat the experiment a million times, you get this pattern. But on the million plus one attempt, where it will go, we don't know. We just know that the odds are high when the function is high, or the intensity, and the odds are low when the function is small, and the odds are zero when the function is zero.
So we do know, just like when we know when we roll a dice, there's only 6 faces on the dice, right? So you know that there's a certain limited number of possible outcomes for how the dice will land. And the same is true here in the sense you could predict beforehand that what's the probability that you threw the photon near the surface, and what's the probability that went through the middle. So that you could figure out, and that's essentially what decides this, because this pattern isn't this even pattern. There's 90% of the light right here in the middle, especially for the single slit. Gigantic amount of the light is right there in the middle. So you already know that there's something that's a variable controlling, and the controlling variable is how close was the photon to the surface. That'll decide what the likelihood is of where it's going to end up.
So the role of the wave is to determine the probability that the photon will arrive at some point on the screen. And the probability.
So that's all just based on their assumptions. And again, the probability won't be some standard probability. You can change the probability by changing any one of the variables. And the most important variable is shoot the photons right next to the surface, and you'll radically change the likelihood of creating a fringe photon. You'll go from 10% of your photons being fringe photons to 90% of your photons being fringe photons. So just shoot the light on the edge of the surfaces, not in the middle, and you're going to have a high percentage of fringe photons and a very low percentage of straight through photons.
But it is computed by adding one wave function to another wave function and then squaring. So you got to be very clear. If someone says to you, is the photon a particle or a wave? Make up your mind. What is it? Well, the answer is...
Well, again, the answer is that waves don't really do particle, but particles can look like waves.
It's not going to be a yes or no question.
Yeah, it is.
People always ask you, is matter made of particles or waves, electron particles or waves? Well, sometimes the vocabulary we have is not big enough to describe what's really happening.
And sometimes it is, and sometimes you just make mistakes, and sometimes you just make something simple more complicated. The universe is made out of push or pull. It really is a real question. It's a push universe, not a pull universe. It's not a push-pull universe. It's the same argument here. This isn't a wave-averse. It is a clump-averse, okay? And clumps can look like waves, but they're never waving. Okay, they themselves can't wave.
It is what it is. It is the following. It is a particle in the sense that the entire energy is carried in these localized places, unlike a wave. When the wave hits the beach.
So he's just using the guide dog kind of theory that somehow the wave guides the particle to the landing zone. So a bunch of radar and other stuff is telling the particle where it's supposed to go, some kind of nonsense like that. When no, the particle is just traveling straight line vectors, and the only thing that's going to change its direction is it has to have a direct interaction with an electron.
The energy is over the entire wavefront. This wave here is not a physical wave. It does not carry any energy.
So again, what's the point? It's not a physical wave. It doesn't carry any energy. It's not a real thing. It's just magical, made out of what? Fairy dust, hobgoblin juice, gremlin mush, Tinkerbell, skin cells. I mean, what the fuck? It's just some sort of fake thing then. Why talk about physics and then say, well, it's made out of this fake thing? It's just, there's no point. It's not physics then. It's not physical. It's just magical. You might as well just say it's magical.
It's not even a property of a beam of photons. It's a property of one photon. Here's what I want you to understand. You send one photon at a time, many, many, many times.
Rays. So the photons have to be understood as a clump of ray. It's an amount of quanta, energy quanta. Okay, and all you really can do is change how much time that clump takes to hit the surface. And the faster you can get all the little clumps to hit the surface, the more damage you can do to the surface.
And you get this pattern. Each time you throw the die and ask where will the photon land, this function is waiting to tell you the probability it'll land somewhere. So we have to play this.
So again, it's just fake because every photon isn't affected the same way. And that's proven by the single impediment versus the single slit opening. Same exact mathematical dimensions, you get a very different pattern on the other side. One pattern says 90% of the photons goes very straight right through, and the other pattern, only 80% are bent.
This game in two ways. It is particles, but its future is determined by a wave. The wave is purely mathematical. You cannot put an instrument that measures the energy.
Yeah, it's just silly. Purely mathematical, no. It's a physical universe. You have to account for things. You can't just say it's a wave. So part of the wave goes to Venus, though, right? The photons bounce off of me, they go out the window, and they fly all the way to Venus, the wave component. So the wave component went all the way to Venus, but it was only the wave component, so it doesn't mean anything, even though it went all the way to Venus. But it's invisible and non-existent. But it told the photon to bounce back and go through this camera. But the wave portion went all over the place. I mean, it's just too silly.
Energy due to that wave. It's a construct we use to determine what will happen in this experiment. So we have no trouble predicting this experiment, but we only make statistical predictions.
Right, and the predictions aren't as accurate. And Young's diagram was really diagramming a single slit, not a double slit. His averages, if you went from the middle of the slit and did the numbers, you're not going to get the right answer, because the right answer is actually going to be from the outside dimension. So if you actually took the Young analysis and had the wave in the middle of the openings, you're not going to get the right answer. The only way to get the right answer is to use, in the example of Young with the infinitesimally small slits, is you have to use the outside dimension, because those are the only 2 point sources that are relevant, are the two outside ones. The inside ones are the ones you've ruined by making them so close to the outer dimension. By making them almost the same spot in space, the 2 points can't be distinguished. They can't make a wavelength of difference. And so I went through that all in part one. But that's the key part of it, is that Young's analysis wasn't actually mathematically strict. Didn't get the right answer.
So if someone tells you, I got light from some mercury vapor or something, it's got a certain wavelength, therefore a certain frequency, I'm going to take 2 slits, and I'm going to send the light from the left, so weak that at a given time only 1 photon leaves the source and hits the screen.
So again, this weak light thing you can't really do that. And the fact is that you're never doing a single photon. You're just creating a bunch of obstacles in the way of the light, and then you end up sending little pieces or little fragments of the photon or getting through all of the particulates you put in the way. So if they actually did it by retracting the light, that is moving the light further and further and further back, at least then, okay, they'd still have atmosphere to travel through, but they wouldn't be traveling through a filter that's a slit experiment. Every time you create a filter, you're just creating a bunch of slits. A half silvered glass slide that's a beam splitter is a bunch of slits. So yeah, the light that bounces off the silver part doesn't go through a slit. The light that goes through the opening where the silver isn't, that's the light that's spreading. Really important stuff that they've got completely wrong.
What will happen? We will say we don't know what it will do. We don't know where it will land. But we tell you if you do it enough times, millions of times, soon a pattern will develop. Namely, if you plot your histogram on where everybody landed, you'll get a graph. It's the graph that I can predict. And how do I predict that graph?
Just by knowing the distance between the point sources. And the point sources are the surfaces. They will perfectly predict your graph.
I say, what was the energy momentum of a photon? If it was P, I would introduce a wave whose momentum is 2 pi h bar over P. Oh, I'm sorry, I forgot to tell you guys one thing. I apologize. I've been writing h bar and h. I should have mentioned it long back. H bar is h over 2 pi. Since the combination occurs.
So again, it's really just another constant. So you're just saying that you're just changing h bar from 0.6, 0.38, whatever, times 10 to the minus 37, and you're just making it into a different number. You're making it into 2.7 times 10 to the minus 37.
There's so often people write h bar. So you can write lambda equals 2 pi h bar over p or h over p. Doesn't matter. So I've stopped using h. Most people now in the business use h bar. Because the energy is h bar omega, momentum is h bar k. If you want, you can write this 2 pi h k, and k is 2 pi over lambda.
So this is just talking about energy. It's not talking about the intensity. So again, it's just, it doesn't have much to do with this two slit, okay, this h bar stuff. So it's kind of just confusing the two subjects. You don't need to know the total energy of the photon, because the only thing the frequency is going to change is the size of the bars.
Find p is h over lambda. That's how people used to write it in the old days, but now we write it in terms of h bar and k. Anyway, I can make these predictions if I knew the momentum of the photons. The photons were a definite momentum, therefore there's a definite wavelength. I can predict the interference pattern. So where is the photon when it goes from start to finish? We don't know. I'll come back to that question now. But I want to mention to you a historical fact, which is photons were not really found this way by looking at the recoil of a emulsion plate. Just for completeness, I'm going to make a 5-minute digression.
The recoil of. So again, Einstein did talk about that in the later paper. But yes, the paper where he introduced the photon, he wasn't talking about the energy of the photon in the sense of he wasn't talking about its absolute momentum.
And to tell you how
its capacity to move matter.
Photons were found. So they were actually predicted by Einstein. And he got the Nobel Prize for predicting the photon rather than for the theory of relativity, which was.
So it wasn't really predicting the photon. So it's just this use of the word. So everybody knew the word, like light, and it was just waves or rays of light. So they knew it had a frequency, and they didn't have a word. So yes, he sort of popularized using the word photon to describe the idea of the clump that hits the surface, the amount of energy that hits the surface. They're so continuous that it's so hard to say, oh, there's one photon. There's one photon. Because they're constant and continuous. And the only time they're relevant is when there's millions of them for us. I mean, we can't see them unless there's a whole bunch of them.
Still controversial at that time. So he predicted the photons based on actually.
See, this is the wrong word to use, I think. What he explained is that you have to understand them as being quantized, or you're not going to be able to explain, how you're going to make an electron move with them. So how are you going to force an electron off of a surface? You're not going to do it with a wave. You need something that has quantizable energy.
Really complicated thermodynamic statistical mechanics arguments, but one way to understand it is in terms of what's called the photoelectric effect. If you take a metal and you say, where are the electrons in the metal? As you know, most electrons are orbiting the parent nucleus. But in the metal, some electrons are communal. Each atom donates 1 or 2 electrons to the whole metal.
All right, so he's saying that each atom donates 1 or 2, and it's really not the truth. So what it really is that the nucleus is positive. So you have this thing inside the atom that's positive. So if you were saying it's red, let's say, and the electrons create blue light, you can understand that the electrons are on the outside of something that's net positive. So you have little dots of blue, and then you have this bright thing in the middle that's red. And the fact is that the electrons are far enough from the positive nucleus that you could understand that if something was exactly over here, all right, I have the positive nucleus here, I have 2 electrons here, that they're going to see this red and be attracted when they're way over here. They're going to see the positive and want to go towards it. And the fact is they're not going to see these 2 electrons until they get really close to them, and then they're going to see the electrons. Because the nucleus is net positive for a gigantic nucleus. It's much more positive than these 2 electrons. The net positive of the nucleus is much brighter than these 2 electrons. But once the electron gets close, it's going to see these 2 blue electrons and be repelled. So it's going to be stuck here. It can't go here because it's repelling against these 2 electrons that now, once it's close to them at the inverse square law, the closer it gets, the stronger the repulsion. And so that's the dilemma, that there's a bunch of spots that an electron can be where it's not part of the atom, but it still sees the positive nucleus, and it still wants to hang around the atom. So that's what they're doing. They're electrons that are really attached to the metal because they definitely see the positive nucleus. They just can't get to it because there's a bunch of repulsive electrons in their way, but they still are going to stay here. They might jump from here, they might jump to here, they might jump to here, they might jump from nucleus to nucleus, in terms of their viewpoint, but they have to do it by jumping around the electrons. And so they're stuck to the metal. They're just not stuck as much as the actual atomic electrons.
They can run all over the metal. They don't have to be near their parent atom.
So they're not running anywhere, they're not doing any of that stuff. They are sticky, and it takes energy to move them, to unstick them. And the point is, how much energy does it take to get them free, where they're far enough away from the nucleus where it isn't, making them stick.
Yes, they cannot leave the metal. So in a way,
they can leave the metal. You just have to push them hard enough into the electrons. So the electrons are sitting here. This electron's coming in. It's attracted to the positive nucleus. It's getting closer and closer. So you push it in hard enough. It pushes these electrons farther away, and then they push on extra force. So they create more force, and it springs back with even more force. So it springs back, pushing even harder on the electrons. The electron expands, the atom pushes back, and that fires the electron off the surface. So it is all based on storing the energy in the elasticity of the atoms, and then the atoms spring it back in a burst of energy. So they take a slow action and turn it into a fast action.
There's a little tank.
So there's no tank. This is really just describing the fact that the electron is attached to the proton. It's wanting to get to the nucleuses, the protons in the nucleus. It's seeing them. It wants to get to them. So that's all this deficit is indicating. This is how tight the electron is bound to the positive. And what you really have to do is figure out, how do I create enough energy to pop it out? Well, the only way you can pop it out is you actually have to push it in to pop it out. It's like this line he draws at the bottom. You can think of it as a trampoline. What you really want to do is push on the electron into the trampoline so it fires out far enough to get over this cliff edge. So you're really going to put energy in to get energy out.
H, let's say MGH, I want to call W. These guys are some.
So we know that MGH isn't the right definition of energy.
That
was a mistake. Whoops. Yeah, I'll go try to fix that. Alright, I think I'm back or somewhere close.
Let's say MGH, I want to call W. So these guys are somewhere in the bottom. They can run around, they cannot get out. So if you want to yank an electron out of the metal.
So this really isn't MGH. This isn't real gravity. It isn't any of that stuff. This is just a charged effect. So the electron is attracted to the nucleus. It's repelled by the electrons. It's stuck. It can't break into the atom. So it's stuck on the outside of the atom, but it's still attracted to the big giant nucleus. Well, the big giant positive of the nucleus. The strong positive net force coming from the nucleus of the atom.
You have to give it energy equal to W, which is called the work function.
The protons.
So how are you going to get an electron to acquire some energy? We all know electron has an electric charge. I have to apply an electric field, and I know electromagnetic.
So we know there's no going to be an electric field involved. None of that's going to happen. What you're going to do is hit this with a quanta of the energy. It's going to push on the electron, and so this probably takes a new drawing, okay, because this involves more than one atom. More than one atom has to create electricity. You can't create electricity with one electron and one atom. You can't create the phenomenon of a recordable photon without you having more than one atom. More than one atom has to be involved. More than one electron is involved, because what you're really going to do is this tipping point thing. You're going to put energy in, and you're going to put it in here, push it, and then you're going to hit it again and push it, and then you're going to hit it again and push it before it slows down. That's the key. Always before it slows down, before it starts going backwards anyway. And that's the idea of creating electricity, is you always have to keep adding energy, and finally then you'll have an electron moving fast enough that it'll break free. It's just about giving an electron enough velocity where it's not held in orbit anymore, so to speak. It's increasing the velocity, breaking the orbit. It's probably a simple way of analogizing it. If you want to break something out of its orbit, all you have to do is give it more velocity. All right. So I guess we'll call this a part 2, and then we'll add a part 3 and such, and so forth and whatnot.